Now, once I do work on something, it can do what? It can do work on something else, like the wall, right? We have a word for that. What do we call something that has the ability to do work? We say it has energy. Energy is what we call the capacity to do work, or the ability to do work. By pushing the ball, I gave it the ability, the opportunity, the capacity to then exert a force over a distance on something else.
So
I gave it energy.
Are we energy as people?
We do have energy as people. Yes?
So like, let's say that you know how like last year we like did the kickball thing metaphor thing? And so, like when we kicked it, and did it have energy because we gave it like the ability to do work?
You transfer your energy to it.
Absolutely. Yes.
Energy.
Energy.
Yes. Okay? Now, which gives us what we call the work energy theorem.
The work energy.
Yes. Which says that the net work, right, that's the Greek sigma for sum of all work, the net work results in a change in energy on an object. Another way to write it would be W net, right? Same thing. That simply says that when I do work on an object, I change its energy. When I do positive work on an object, I increase its energy. When I do negative work on an object, I decrease its energy. Which you saw with the bowling ball, right? As I pushed it the first time, I got it moving. I gave it energy. I increased its energy. And when I stopped it, I did negative work. And I took away its energy. All right? Yes?
Wait, is that weird E on the left?
It's the sigma for sum of all.
Oh.
Right, kind of like we did net force, the sum of all forces.
So pretty much work equals energy.
Yes, work and energy are interchangeable. We'll go from one to the other all the time. All right? Now, I want you to imagine that I'm trying to move this ball, again, that 1 meter. I've got two options. One, I can lift straight up like I did. In which case, I'll have to use a force of 80 newtons over a distance of 1 meter. Or, I can use a simple machine. What simple machine is that? I could use a lever, but I'm thinking of a different one. How about a ramp, an inclined plane? If I push the ball up a ramp, what does the force diagram look like? Still has energy down, but now the normal force is there, and my pushing force is up the ramp. What's then going to happen to the work I do lifting that ball up the height of 1 meter?
It's going to divide it in half. Like that we did, how it divides it in half on each side. Right. You don't have to wait on the middle.
Good thought. Excellent thought. But it's not. And here's why. What's going to be the end result of the bowling ball? If I do it this way, I have a bowling ball that's a meter above the ground. And if I drop it on my foot, it'll break a few toes, right? But what if I start off over here and I push it up the ramp?
You have to push up and
And I push it up, where does it end up? A meter above the ground. And if I drop it on my foot, it's going to break a few toes. In which case did I give the ball more energy? Same. Okay? Here's the key. Here's one of the take-homes. Simple machines do not change the amount of work you do. You don't get to cheat using a simple machine. You don't do less work. So what's the advantage of the ramp?
It makes it easier to do this.
Why? How? What do you mean by easier?
Because I guess if you're pushing, you're using your legs more than your arms. Maybe? No.
Well, it's how
Good thought.
push up.
Well,
You only
okay.
have to push one direction.
But what's significant about that direction? Yes?
Is it like spread the force needed over a greater amount of time?
Yes, or in this case, a greater amount of distance. Exactly. So I'm doing the same force, the same work, but since instead of pushing it up just the 1 meter here, I'm going to push it up the hypotenuse of the ramp, which is greater than 1 meter. So I get to use what? Less force. And less force is what feels easier. So the work is the same, but by using a greater distance, I get to use less force. Yes, sir?
So, does it make it easier to pick up a box while you're walking? Because you're moving forward and picking it up at the same time? Or is it easier to pick it just straight up?
Well, if I'm just picking it up, it's going to be probably easier standing still, just because I'm not using any of my area to move forward, or my balance, whatever. And plus, is my horizontal motion going to help lift the box vertically? No, those are independent. Yes, no.
How can you do the same amount of work but go greater distance and have to use less force?
Exactly, because if this is smaller and that is larger, I can have the same work.
Okay.
Because it's a trade-off, right? I don't get anything for nothing. I can't cheat God by getting to do less work and moving something from one point to another. But what I can do is make it easier for myself by using less force if I can make that force over a greater distance.
Well, you said the force is greater, if the distance is greater than the force, then the work is less.
No. The force is less, so the work's the same. This goes up, and this goes down, I get the same result.
Are you saying that you use the same amount of work cutting the long scissors than mowing the grass? Or is that...
Oh, that's a little different. Because I get different results. All right, now, look at this. What if I have a box, and I'm dragging it along the floor, and I'm doing so by pulling on a rope that's making a 30-degree angle with the floor. How am I going to determine? If I exert we'll call this a 30 Newton force, and I drag the box a displacement of 4 meters, how much work am I doing? Okay. Yeah, it's 30 times 4 times cosine of 30. Right? Work equals the force times the displacement times cosine of the angle between them. The force is up here, the displacement is here, and so the angle is 30. So the force is 30 newtons, the displacement is 4 meters, and the angle between them is 30 degrees, so cosine of 30 degrees. And when I plug that into my calculator, I get...
Could you go ahead and simplify that? Like, could you put like the square root of 3 over 2 for cosine?
But since I have my scientific calculator, I can use it, right? And I get
103.9.
103.9. for what?
Jules.
Joules of work. Okay? Now, I want you to notice something. By pulling up at an angle, we're doing two things at once. What are they? Good. Sideways and up. We're pulling horizontally like this at the same time that we're pulling vertically like this. Which one of those two lines is actually doing the work?
No, down.
It's both.
Point at the color on your desk. You got those colored squares.
Ooh, it's like
Red or blue or green. Green is both.
green.
Point to the color of the force that's doing work.
Do we lose a finger up our rock since we don't have markers?
That's what I'm using.
Give me like 2 seconds.
Keep those.
Wait, is red less or more?
Red is that.
Oh,
Blue is that. Green is both.
Wait, what are we looking for?
Which one of these forces is doing work? Is it the red one,
Red.
the blue one, or both?
Woo!
It's not going up.
Definitely both. Yeah, that's good.
Okay. It is definitely red.
Yes!
Get on my level.
Because which direction is the blue one? Up. And the displacement is
Come on, guys.
horizontal.
Independent.
What do we know about these? They're independent. My pulling up is not going to do any work horizontally.
So we were.
That's why we use, that's what that cosine theta does. That cosine theta gets just the part of the force that's in the direction of the displacement.
What if you were pulling the box on a ramp? Would it be both?
Ah,
We didn't specify if it was on. Yeah, we didn't. The ground might have been. No.
okay, let's do this.
And so what if?
The ground was all right. But the ground had to be completely level for that to be true.
Oh wait, where's, I can't rotate this? That sticks. So imagine this is on, I'll have to do it this way.
Turn right up.
Yeah. So I'm pulling up the ramp, that's the velocity, but yet I'm pulling with a force that's in this direction, up a ramp.
So it's.
Okay, yeah.
Yeah. There's still this angle theta, and it's only going to be the part that's in the direction of motion that's going to count.
yeah, it's on.
Just dumb.
Exactly.
But isn't it moving over as much as it's moving up?
Oh, good question.
What if you?
Why would you pull up with an angle to begin with? Why not just pull straight then?
Because then you have to be on its level.
Two things. Number one, you have to be on its level, but then, second of all, if I draw a force diagram of this guy, if I pull that direction, and it's sliding across the table, right, so it's got friction, by pulling up some, what happens to the normal force if I pull up a little bit? It decreases, right? The normal force of the floor on the box decreases. If the normal force goes down, friction goes down. So one thing for pulling up is convenience for the direction of the force, but also it decreases the friction by decreasing the normal force.
So would 45 degrees be the optimal angle there?
It might be. Actually, it depends on the coefficient of friction, how large it is, but yes, it'd be something close to that. Now, what you definitely don't want to do is what?
Pull straight up, pull. That's
That's ridiculous.
You don't want to push like this, right? You don't want to push down and forward.
Yeah.
Because my down part's not going to move it that way, and it's only going to increase the normal force, which increases friction.
Feel like on ice or something.
All right. Then it would just be a convenience thing in the direction of